and we can change it to DC machine, AC machines. Okay, so in DC, basically machines can convert electrical energy to mechanical energy or mechanical energy to electrical energy. Am I audible?
Sir, you are audible, but just voice is cracking sometimes.
Cracking sometimes. Okay, just hold for a minute.
Okay.
Now is audible properly?
Yes, sir.
Okay, fine. So I told already if a mechanical energy can be converted to electrical energy or an electrical energy is converted into mechanical energy, so anything that converts mechanical energy to electrical energy or electrical energy to mechanical energy, that are called basically machines, electrical machines. Okay, so you can see in the diagram, if if mechanical energy is converted into electrical energy, and that thing or that assemble of element is generator. Okay, basically when input to electrical machine is electrical energy and the output is mechanical energy, that basically is called electrical motor, and in this process we are using mechanical energy to get the electrical energy, that is called generator. Both generator and motor comes from category of machines. Okay, so how we construct the DC machine? So there is, I think this construction part is not in your syllabus, but still, for better understanding the questions, we'll go through little bit of construction of DC machines. Okay, so diagram here. Basically, the main parts of DC machines are, or the main part of the motor and generator. So the construction is similar for motor or generator. The construction is almost similar, but the principle is little bit different. So you can see in this diagram. So its main part is called yoke, then pole core, pole shoes, field winding. So you can see here the outer layer. This outer layer is nothing but is called yoke. Okay, basically it is a frame. Then there is you can see this is the pole. You can see the pole. Okay, any issue? You can see here there is a north pole, south pole. These are poles, and there are some windings here. That is called field winding. Okay, similarly, pole shoe is there, armature core is there, and this part is called armature. This part is called armature, and this is called commutator. This is called commutator. Similarly, armature winding is there. Then process is there, bearings are there. So let's see one by one. So basically, you can see this is the yoke, or this is called outer part of the machine, which is providing mechanical support. Sometimes the yoke is also called frame, and this is made up of cast iron or sometimes steel, cast steel. Then this is your pole. I already told about poles, north pole, south pole. You can see here. So this pole comes under pole and pole core. This is basically electromagnet. Remember, this is electromagnet, not permanent magnet. So whenever we produce electricity, at that time it will behave as a magnet. So nothing to see here. You can see this is pole and this is called pole shoe. This is called pole shoe. So you can see here. So you can see in this diagram, these are nothing but the poles and pole shoe. So there are some windings are here. So when electric current will flow through this, so these poles are behaves as a north pole or south pole. So we basically provide a DC here. DC supply here. Okay. Then it comes under armature, or then the coil, the armature shaft. Then this is the tooth and slot. Okay. You can see in this diagram, and you can see this type of figure. You can see in this some electrical shops also. So inside this, we have a copper winding. You can see this is the figure. You can see copper windings are here. This is called armature or armature winding. The armature conductor are interconnected to the armature winding. Okay. So these are some construction parts of this DC machine, and these are called commutator. So the commutator is connected here. You can see here. This is commutator. What is the function of commutator? What is the function of brush? That I will going to tell later. So function of the commutator is a mechanical rectifier. You can see here. It is a mechanical rectifier that converts AC alternating current induced in the armature conductor into unidirectional current in the external loader circuit. So you can see here, I already told we use basically generator to generate AC alternating current, but I'm using the term here DC machines or DC generator. So here I want a DC, but the function of this generator is that will basically get AC. So here I'm using a device called commutator, which will use as a rectifier, which will provide DC from this AC. Okay, and this is the brush. These are the brush. This is carbon brushes. So these brushes collect the current from the commutator and apply it to the external load. So basically, it is a connecting device from the commutator to the external load through which current will flow. This is basically wear and tear material. After some day, these brushes will tear up and you have to provide a new brush. Okay, so this is the total diagram of the DC machine. Here are some more figures. Okay, you can see this diagram: North Pole, South Pole, commutator segment, then interpole. Okay, then we'll come to the what is the working principle of generator. Okay, so an electrical generator is a machine that converts mechanical energy into electrical energy. Whenever a conductor, I already told about what is the working principle. Whenever a conductor cuts magnetic flux, a dynamically induced EMF is produced according to Faraday's law of electromagnetic induction. Okay, so in intermediate also you have studied this. Whenever a conductor cuts the magnetic flux, I already told when there is a north pole and there is south pole, magnetic lines of force are going from north pole to south pole. Whenever you rotate a copper coil inside the magnetic field, a EMF will be induced in this coil. Okay, and that EMF will be induced according to Faraday's laws of electromagnetic induction. Okay, and the direction of induced EMF is given by Fleming's right hand rule. Okay, remember in generator we are using Fleming's right hand rule. Okay, all of you please mute your mic. Okay, and the amount of voltage. So the amount of voltage generated depends upon the things like the strength of the magnetic field and the angle at which the conductor cuts the magnetic field and the speed at which the conductor is moving. Okay, and the length of the conductor with magnetic field. Okay, so here in this
Hello.
generator, the induced voltage or the voltage we are getting in from the generator that depends upon the so many things. So therefore, the essential components of the generator are a magnetic field, a moving conductor or conductors has to cut the flux. Okay, so as I told you earlier, that Fleming's right hand rule is applicable to find out in which direction current will flow. You can see the Fleming's right hand rule. The thumb shows the direction of force, and this first finger is showing the direction of the magnetic field, and this middle finger is showing the direction of the current, or this second finger is showing the direction of current. So by using this, so we can get the current. So you can see the north pole, south pole. You can see the direction of electric field is like this, and we are moving the conductor is like this. The moving the conductor is like this. So it is rotating like this, and I'm getting electricity which will flowing like this. Okay. So you can see here. So these are some theory. I'll provide this theory to you. Just go through this. Okay. You can see here. So how the north pole or south pole is placed, and there is a copper coil called A, B, C, D. And when this copper coil is moving through this axis A and B, if it's rotating like this, then how the current is flowing. You can see the direction of rotation is providing the direction of rotation, and always the current is providing from C to D and A to B. You can see this is the direction of flux and this is the direction of induced current. Okay, so you can see always the current is flowing in this direction. Always current is flowing in the same direction. Okay, okay. You can see I already told this diagram in the class. For one rotation of this coil, full rotation from 0 to 2 pi, I'm getting a AC waveform which is like this. Right, this is 0, this is pi, this is your 2 pi. Getting waveform like this, and this is called one cycle. Okay, but in case of DC, I already told I'm using a commutator, and commutator is a mechanical rectifier. The commutator is a mechanical rectifier. So by using this commutator, I'm always getting a waveform is like this. You can see this is a DC, this is not AC. So due to this commutator, the first half I'm getting waveform starting from 0 to pi. Then for the second half, again I'm getting waveform from pi to 2 pi. So that's why it is called DC generator. It is called DC generator, or I'm saying the DC machine. I'm using here DC machine. So due to the commutator, I'm always getting a DC basically. Okay, so you can see this is the what is the use of slipping commutator here, and getting how I'm getting always a positive waveform, or the waveform always in the first half. Okay, okay. Next is the effect of additional turns. Okay, you can see in this previous figure, I am taking basically a single coil. I'm basically taking a single coil. What happened if the number of coils are increased? The number of coils are increased. Okay. So to increase the amount of output voltage, it is common practice to increase the number of turns where in each loop. So if we increase the number of coils here, the amount of output voltage will increase. Okay, the amount of output voltage will increase. So we can take an example here. If a loop contains 20 turns of wire, so in one loop I'm getting 20 turns, the induced voltage will be 20 times greater than that for a single loop. If for a single loop I'm getting a 2 volt, if for single loop I'm getting a 2 volt, for a 20 turns of wire I'm getting a 20 loops, I will get a 40 volt. Okay, so that's why instead of one single copper coil, I can use number of turns. So number of turns will increase, means the output voltage also increase. Okay. Then coil winding or element. So basically we are using two types of winding. One is called lap winding and another is called wave winding. Okay. So there is a one called lap winding and another is called wave winding. Okay. Just remember the lap. Now this most important part will come. EMF equation of DC generator. So from the EMF equation of DC generator, we'll get some numerical. Basically, we'll get one or two numerical or maximum of 10 to 20 marks question. So to derive the expression of a EMF generated in a DC generator, let us consider that phi is the flux per pole in the Weber. This is the unit. So phi is called flux per pole. Next is that Z. Z is the total number of armature conductors. It is the total number of armature conductors. So you can see the armature is there. How many conductors are there? Number of conductors are there. That is denoted as Z. Next, the number of poles. P is the number of poles. How many poles I am putting? North pole, south pole. That is the number of poles. A represents number of parallel paths. I told here there is two types of winding. One is called lap winding, another is called wave winding. So the number of parallel paths is 2 for wave winding. That is always fixed. And for lap winding, this is number of poles. So for lap winding, this is A equal to P. The number of parallel paths is equal to number of poles. And N represents speed of the armature in RPM. So this is called revolution per minute. Revolution per minute. N represents speed of armature in RPM. Okay. And EG represents the EMF of the generator. So what is the generated EMF in the DC generator? Okay. So these are some terms you need to remember here. Then flux caught by one conductor in one revolution of the armature. So I already told flux per pole is phi, and flux caught by one conductor in one revolution of the armature, that represents d phi. So d phi basically it is p into phi. So p represents the number of poles and phi represents flux per pole. So the d phi equal to p phi. And time taken to complete one revolution, that is called dt. Time taken to complete one revolution, this is called dt, and this is 60 by n, where n represents the speed of the armature. This is 60 by n. Okay. So EMF generated per conductor. So EMF generated per conductor equal to d phi by dt, or I can write it d by dt. So it basically np by 60. This is np by 60 volts. I don't know why this equation is not coming. Okay. I don't know. Basically, this is d by d phi by dt equal to p phi equal to here np phi by 60 volts. So EMF generator. So EMF of the electromotive force of a generator I can represent equal to EG, that is EMF for conductor into number of conductors in a series for parallel path. So I can write down here EG equal to phi n pi into Z into A. So all of you can write down in your class note. So this is the formula. After that we are going to solve some numerical. So EG equal to phi np Z divided by 60A. Okay, and you can write down finally here, where A equal to 2 for wave winding and for A equal to P for lap winding. All of you can 60. Just write it down. Once complete, let me know whether you completed or not. Everyone completed?
Yes, sir.
Everyone completed, please respond.
Yes, sir. Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay. Next, just write down some questions here. Write down first question. An eight pole wave, an eight pole wave connected armature has 600 conductors and it driven at 625 revolution per minute. If the flux per pole is 20 milliweber, determine the generated EMF. All of you please write down the question. First, you will find it given here. What is given here? 8 pole. So number of poles is given. So P equal to 8 here. We have connected. So this is a, so the winding is wave type. So if wave is there, so I can write down the A equal to 2. So what is A here? A is the number of parallel paths. So number of parallel path A equal to 2. Okay. At 600 conductors. So Z represents the total number of armature conductors. So Z equal to 600 here. Okay. And it is driven at 625 revolution per minute. N is also given here 625. Okay. And if the flux per pole is 20 milliweber, that means phi is also given. Flux per pole is given 20 milliweber. 20 milliweber, I can write down here 20 into 10 to the power minus 3 Weber. Okay. So these many things are given and they asked determine the generated EMF. Okay. Determine the generated EMF. All of you please open your calculator. So EG equal to using this formula phi N P Z divided by 60A. Okay. So I can use it. You can use your calculator and tell me the answer here. So I'll get 20 into 10 to the power minus 3. N is given 625.
Five hundred volts.
1800,
500.
500.
500, sir.
Okay, okay, let me calculate.
500.
How much you got?
Five
How much you
hundred.
got? 500.
Sir, you didn't write the value for Z.
Z, where is Z? Okay, correct. Now calculate what is the value.
500, sir.
So all of you got 500 volts. Next question. Write down the next question. All of you copied?
Yes, sir.
Write down the next question. A 4-pole generator has a lap-wound armature with 50 slots with 16 conductor per slot. The useful flux per pole is 30 milliweber. Determine the speed at which the machine must be driven to generate an EMF of 240 volts. Okay, so what is given here? Let's write down the question. A 4-pole generator. A 4-pole generator means P is given 4. Has lap wound. So lap wound means what is the number of parallel paths? For lap wound equal to number of parallel paths A equal to P, that is 4. With 50 slots, with 16 conductor per slot. So total number of conductor, I can find out the total number of conductor 50 into 16. So I'll get 800. And phi is given how much? 30 milliweber. So 30 into 10 to the power minus 3 Weber. Determine the speed at which the machine must be driven to generate EMF. So EG is given here 240 volts. Okay, so need to find out what is N. So basic one, first write down EG equal to EG into 60 into A divided by pi Z P. So tell me the answer. What is the answer you will get here? 240 into 60 into 4 divided by 240 into 4 into P. Z is how much? Sorry, Z. This is Z. Z is 800. Just tell me the answer. What is the answer?
Sir, maybe phi is equal to 13 into the minus 3.
How much?
Phi, you have written 240, it will be 30 into the minus 3.
Okay, wait. Yes, that's correct.
Answer is 600.
I don't know the answer. Wait.
My answer is coming as 600.
So that must be your 30 into 10 to the power minus 3. Anyone got the answer? 600 is the answer.
Yes, sir.
N
600.
equal to 600.
Yes, sir.
Okay. So all of you just write down.
600, sir.
If you have already written, then we'll go to the next question. The next question is given: an 8-pole lap und armature has 1200 conductors and flux per pole of 0.03 Weber. Determine the EMF generated when running at 500 revolution per minute. Just do it by yourself and tell me the answer. Or you can write down question number 3 and 4 at a time and tell me the answer for question number 3 and 4. What is 300 volt? What is the answer for question number 3?
Sir, 300.
So for question number 3, the answer is 300, right? So 300 volt is the answer for question number 3. How many of you got? Got 300. Irfan Khan,
Yes, sir. 300.
7079, Sayan Siddiqui, Siddharth Menon,
हाँ सर 300.
Sahas, Harsh Mishra. Okay. What is the next answer for the fourth question? A DC generator running at the 300 revolution per second. See the question. 300 revolution per second, not in minute. Generates an EMF of 200 volts. Determine the percentage increase in the flux per pole required to generate 250 volt at 200 revolution per second. Okay, write down the question and I think do it by yourself. I'll discuss in the offline class. Just write down the question here. Write down the question only. Okay, we'll go to the next section. So there are different types of DC generator is there. So like separately excited DC generator, self-excited. So in self-excited there is a series wound, shunt wound generator, compound wound generator. In compound wound there is a short shunt and long shunt. So I think this is we are not covering in our syllabus. Okay, so this is the diagrams of the DC types of DC generator. So you can see here DC generator broadly divided into separately excited, self-excited. Then in self-excited we have shunt wound, series wound, compound wound. So compound wound also again divided into short shunt and long shunt. Then we'll go to the working principle of DC motor. Like generator, there are three. So whenever electric, so I told, so both DC motor and DC generator comes under the category of machine DC machines. So in DC motor, basically, we use input as electrical energy to get the output as mechanical energy. So, the working principle is that whenever an electric current is passed through a coil in the magnetic field. Okay. So in the inside a magnetic field, a coil is there, and if you pass electricity, so it produces a motion or electrical mechanical force. Okay. The direction of the mechanical force is given by Fleming's left hand rule. Remember, in DC motor, we are using Fleming's left hand rule, and in case of DC generator, we are using Fleming's right hand rule. Therefore, the essential components of generator are magnetic field. So this is not the motor. Are magnetic field and moving conductor or conductor are to cut the flux. Okay, so here I am using Fleming's left hand rule. You can see in this diagram. So I am using Fleming's left hand rule. So you can see. So this thumb showing the direction of force, and this first finger is showing magnetic field. Second finger is showing the direction of current. Okay, you can see here the setup is similar to the DC motor. So if a current will flow through this coil, then the coil will move like this up and down. So it will put a mechanical motion of electricity. Okay. So now the next thing will come back EMF, or it's called counter EMF. Okay. So you know already, if I move a magnetic coil inside if I move a copper coil inside a magnetic field, and EMF will be generated. But what we are doing in machine? In a machine, we are providing electricity to the coils, and using the Fleming's left hand rule, the coil will move. So when the coil will move inside a magnetic field, due to the Fleming's right hand rule, an EMF will be generated. So that EMF is called back EMF. You can see here, when the armature of a DC motor rotates under the influence of the driving torque, the armature conductor rotates under the influence of the magnetic field, and hence an EMF will be generated like a generator. Basically, we are giving input as electricity so that we can generate a mechanical energy or mechanical force or rotation. But due to this rotation inside a magnetic field, EMF will be generated. So that EMF is called back EMF. Why it is called back EMF? Because it is opposite to the direction of the applied voltage. So according to Lenz's law, so that back EMF or a counter EMF is called EB or generated as EB, and EB is always less than V. That means supply voltage. This is called supply voltage. Supply voltage is always greater than the back EMF. This is back EMF. Okay. So the net you can see in this diagram. This is your symbol of a DC motor, and I'm providing a supply voltage here V. I'm providing a supply voltage V here. Okay. So this is your EB, and there is a armature is there, and this armature current. So inside this armature, so I am providing current is flowing here IA. You can see the current is flowing IA. So I can write down. So net voltage equal to net voltage across armature circuit is nothing but V minus IB. So this is V. This is your EB. Okay. So the net voltage across armature current is V minus EB. So the armature current is nothing but, you can write down. So IA RA equal to V minus EB. So this is your armature current, and RA is the armature resistance. The armature resistance. This is the supply voltage. This is the supply voltage, and EB is the back EMF. EB is the back EMF. Okay. So using this formula, I can find out what is back EMF, what is supply voltage, what is armature current, what is armature resistance. So this is the formula you need to remember. So in the next class, we will going to discuss about torque equation. Okay, so we're going to discuss about torque equation of DC motor. We're going to discuss about torque equation of DC motor, as well as we'll solve some numerical. Okay, solve some numerical. Okay, and some numerical I will provide you. Just write down in your class notes. Example, just write down. The books also I will provide. Example 26.8, example 26.9 of BL Thereja book. BL Thereja, volume 2. Okay, just write down. So this is one book you have, and another book I will provide. 41.4, 41.3. These two examples also you can solve of the books. The author is Hughes. Okay, I'll provide these two books. Please write down this one. Go through these examples. Okay, and if you have any doubt, you can ask me in WhatsApp or you can mail me. So maybe tomorrow, if I'll get time, I'll take another class for DC motor, for the torque equation of DC motor. Hardly I will take 30 to 40 minutes maximum. Then we can go for your AC machines or transformer. Okay. So just write down the examples. I'll provide the books in WhatsApp. Okay. So up to the we can conclude our class today. Today's class. If you have any doubt, you can write down in chat box or you can mail me. Okay. So I'm ending the session.
Sir, can you please share this this PPT or slides?
Yes, yes, I'll share. I'll share.
Yes,
Okay,
sir.
thank you.
Can you send the recording of this class? Who is asking? 7 on 7.